Okay, so we've talked about limits. We've talked about how we can evaluate limits using graphs and tables. And so we're going to move into the part where we talk about how do we do this stuff algebraically? How do we get an exact answer without having to rely on a graph or a table? Graphs and table are very useful, but sometimes they fall way short. So a couple things. So first of all, we need to talk about places where limits fail to exist, places where limits don't exist, right? And I want you to kind of call you back to that, that mode of thought that we were in a couple days ago, where we're talking about limiting behavior and not actual behavior, right? So remember, the key point with limits is that we never actually get to the point we're approaching. It's just, what does the ant anticipate the value of the function is going to be when he gets there, right? And just think of those ants crawling along the functions, those blind ants. Where do they sense they're going to step? Well, does it make sense that you couldn't have a limit at a place where there's a gap in the function like this, right? Because the behavior is differing from the left and the right. An ant approaching, in this case, a value of 0, an ant approaching a value of 0 from the left is going to anticipate stepping there. And so the ant from the left is going to say, oh yeah, well, the limit's -1. Whereas an ant approaching from the right would anticipate stepping there and say the limit is +1. Well, who's right and who's wrong? Neither ant should have some elevated preferred status, right? They're on equal footing. And so if they both anticipate different places, then what's that tell us? Well, the limit doesn't exist. There isn't a single place where ants from either direction could agree they're going to step. Okay, so this is one type of place where limits fail to exist, when we get different right and left behavior, which we could just call a gap in the function. Okay? All right, another place where limits wouldn't exist would be if we have this asymptotic behavior. What if we're bumping up against an infinite asymptote? You see the problem there, right? Even if the behavior is the same from the left and the right, so both ants are climbing this infinitely steep mountain, are they ever going to be able to say, okay, well, there's a point we think we're going to step on? Doesn't work, does it? Because the closer they get to 0 in this case, the further up they go, right? It never settles down to a place where they could say, aha, I think I'm going to step there, because this, that there would be infinitely high, and infinity is not a number, right? That's not a place. And so we'd say that here's another instance where we can't have a limit because there is no point that we actually approach. It's unbounded asymptotic behavior. Okay, so those are the two big ones. There are some other weird ones. I don't want to spend too much time on this, but let's just take a second here. Gosh, I can't. All my Desmo, I've got a link to something really good here, but I bet it's not going to work. Oh, it did. That's crazy. Now, why was I able to get by the little barrier there? I don't know. That's strange. So let's look at a couple things here. Let's look at sine theta. Okay, that's just a sine graph, right? From last year in trig, you guys looked at that kind of stuff a lot. Just an infinite oscillating function. What's the maximum value of that function? 1. What's the minimum value? -1. Okay, and it just swings back and forth between those infinitely, right? Okay, well, let's look at what happens. What happens if I multiply the angle? If I multiply the angle, and this time we're going to call it x, what if I multiply x instead of theta? What if I multiply that by a? Okay, well, if a is 1, it doesn't do anything, right? The two graphs just line up. But what if I make a bigger? What if I make a something like 2? Now, I want you to just think carefully about this for a second. What's that going to do? And this is kind of a significant relationship that we want to build our understanding of here. What if I take this slider here and I drag it over to where a equals 2? So then I'm taking the sine of 2x. What is it going to do to that red sine graph? Okay, is it going to change it this way? Okay, so it's, okay. It can't change it vertically, can it? How come? Somebody articulate that, please. How come it's not going to change the amplitude of the graph if I change what I'm multiplying x by inside the sine function? Say it again. Okay, I'm not multiplying anything out front, and that's where the amplitude would be affected, right? If you think about a function like a machine, it's got some inputs and some outputs, right? We've got this sine function. We know what that looks like. And the sine function, we're inputting angles into the sine function. And the sine function does its job and spits out the sine outputs, right? It does not care where those input numbers come from or how they get there. It just knows that if the input value is pi halves, it's telling me that the output is going to be 1. If the input value is pi, it tells me the output value is 0, right? It just blindly follows those rules. Well, if I multiply the x by 2, the input variable x by 2, then the sine function doesn't care. When x is equal to pi halves, 2 times pi halves is pi, right? So the sine function would be seeing an input value of pi, even though the x value is only pi halves, right? Well, what is the sine going to do? Well, the sine knows that it's already gotten up to sine pi, which is 0 output, but the x value that I input, which is where I would graph this point, was only at pi halves. So what do you think then? Is that going to stretch or compress that function? If I'm only inputting an x value, so when I go to make my point, the x value that's my input is pi halves, but because I'm multiplying that by 2 inside the sine function is already seeing an angle of pi. If I input 0, the sine function sees 0, right? So we know that the red graph and the blue graph that sits behind it are going to line up there, aren't they? Right? But with the blue graph, I had to go clear out to pi to get to that point, right? With the red graph, because I'm multiplying all the x values by 2, I only had to input a value of pi halves for the sine function to see an angle of pi. So what's that doing then? Is it compressing it or is it stretching it? Okay, I'm seeing some stretching. I'm also seeing some compressing. Let's take a vote. What do you think? Let's go thumbs up is stretching, thumbs down is compressing. Ooh, what do we think here? Okay, let's just see. Let's just see, and then let's see if we can explain it. So if I make A bigger, look what it does. It compressed it, didn't it? Okay, now see if you can wrap your brain around that. Why did it do that? Well, it did that because effectively it kind of accelerated the rate at which we're pumping angles into that sine function. If I multiply it by 2, all the x values are being doubled, and so it's seeing angles twice as fast, isn't it? You see what I'm saying? So it's going to compress this thing a little bit. So that's the effect it has. This is just a little trig review, right? But that's the impact it has on the function. Okay, let's try something different then. And if I went down to 0.5, then I'm cutting in half the rate at which we're feeding angles into that function, and so it should stretch it out, and we can see that too. Okay, give me thumbs on that. Thumbs up, thumbs down. Is that making sense? Okay. Now let's try something different. Let's try the function y equals x to the b, where we're going to put a power in there. We're going to take x to a power. Well, right now, b is equal to 1. X to the 1 is the same as x, and so it looks exactly like y equals sine. I'm going to make, maybe that theta is confusing. How about if I just make it an x? Whoops. If I just make it an x. Okay. And so we've got this. I don't know why that's behind it now, but oh well. Anyway, so now we've got this green sine x to the b. Well, what's going to happen if I make b a value bigger than 1? What if I start squaring the x's? What's that going to do to the input values? So instead of, if I input a value of 1, 1 squared is 1, right? So if I inputted an angle of 1, which is kind of strange, right? What's 1 radian? You know, it is a value though, right? The two functions should line up there. But what if I input a value of like pi for x? If the x value is pi and I were squaring the x value, what angle would the sine function be seeing? Say it again? Not the square root, the square of pi, right? Like if I were making this, if the b were a 2, so it's y equals sine of x squared, then whatever x value I'm inputting, because I'm doing something to it inside the sine function, I'm squaring it, that means that the sine function is going to be seeing the square of that angle. Well, pi squared is a lot bigger than pi, isn't it? Right? What if I put in a value like, 100 pi? If I put in 100 pi, well, 100 pi squared is a really big number, right? So it's going to be a little different than just simply stretching or compressing this time, isn't it? Right? The bigger the x value, the faster the angle's increasing. And so what's going to happen is I move out along this function. What do you think? Let's take a look. Look what it does. Okay, it's going to really start compressing that function, but it's going to be variable. The further out I go, the more compressed the wave train's going to be because the angles start to increase faster and faster and faster, right? Whereas, look in here. For values less than 1, if I take 0.5 and square it, 0.5 squared is 0.25. It actually made it smaller. So it's kind of doing two things at once. For values less than 1, it's stretching the function, but then as the values get bigger than 1, it's compressing it, but more and more as we get further away. Okay, well, why are we doing this? Well, here's the point of this. Why are we spending all this time? I think it's nice to see that. That's, if you go into, you know, a math-related field like physics or electrical engineering or something, I mean, you work a ton with this kind of situation where you're using trig functions where you get, you know, you're manipulating the wave trains of trig functions. So it, you know, you may use this someday. But where I really wanted to go with this was, what if I have sine of 1 over x? Okay, what's that going to do? Think about that one. This is what we were climbing towards, is trying to visualize what's going to happen with the reciprocal of x, 1 over x. Now, what happens as x gets really big this time? If x were 10, 1 over x, the angle the sine function sees would only be 1/10, right? If x were 100, it would be 1/100th. If x were 1,000, it would be 1/1,000th. If it were 1,000,000,000,000, it would be 1 over 1,000,000,000,000. Well, isn't 1 over 1,000,000,000,000 a really, really small number, right? Kind of approaching 0, okay? So out here, far out on the function, it's going to really start to stretch this thing out infinitely, right? It's just going to approach, it's never actually going to get to a value of 0, but it's going to try to get to that value of 0 as x gets bigger and bigger and bigger, right? Everybody see that? Okay. But what happens for values less than 1? What if x were 1/10? 1 over 1/10 is 10, right? What if x were 1/1,000th? 1 over 1/1,000th is 1,000. What if x were 1/1,000,000,000th? Well, that's going to make the number inside 1,000,000,000,000. So as x gets smaller and smaller and approaches 0, what's happening to those numbers inside the sine function? They're getting bigger. They're just increasing astronomically, right? And so the number of swings that we see in the function is just going to increase forever and ever as we approach 0. And we get this bizarre oscillating behavior, which is the third type of limit that a third type of situation where limits cannot exist. This is a really rare one that you'll probably never see. It probably doesn't even come up on the AP test, but it's really interesting. That's what it looks like. Isn't that weird? Let's stretch this out. And what you're going to find is it's not very satisfying to stretch this out because it never fixes the problem. So if I go into Desmos, and this is really handy to do, just kind of watch how I do this stuff because you're going to want to do this stuff too. I'm going to make the x-axis this time just go from like -1 up here to 1. So we really stretch it out, but notice it doesn't do any good. This thing still oscillates infinitely in the middle, right? Let's even go further with that. Let's make the x-axis go from -0.01 up to +0.01. Doesn't help, right? So why doesn't a limit exist here? As ants approach 0 from the left and the right, are they ever going to be able to agree on a place where they're going to stand when they get to 0? No, because the ants just start oscillating more and more and more and more, and they'd have to go through an infinite number of oscillations before either one of them could ever get to 0, which is of course impossible. You can't go through an infinite number of oscillations because it's infinite, right? Isn't that weird? But that's the third type of function that fails to exist, is that oscillating behavior. Okay? Where would you see that? It's not very often. It'd be something like this, like a sine of 1 over x, where the input is going to have a bigger power of x on the bottom than the top, the input to some function. Okay? And it'd have to be like a trig function, something that's oscillating like that. Okay. So just a little, I'm going to draw your attention to something. There is potentially a pitfall when you're trying to look at graphs of these things, especially with the TI 84s. They don't have the resolution that Desmos does. It leverages all the processors in your computer or your Chromebook or whatever to draw these pictures. But like if I wanted to graph sine of 1 over x, probably the newer TIs would do a little better job than that, but that's kind of what it's going to do. But understand that that's really not a very good representation of what the function's doing, right? It just doesn't have the resolution to give you a good graph. So always be leery about what graphs look like on technology. Just like the other day, remember they didn't show the whole. Either it did or it didn't on the function, depending on where we happen to set the boundaries, and that's not very reliable. Okay, so am I on the wrong one here? Let's see something. No, it should be okay. Yeah, and I'm not going to go into this Dirichlet function. We don't need to spend time on that. So evaluating limits analytically. Here's where we kick into this new phase, right? So without graphs or tables, it gives us exact answers, not just decimal approximations. So it's much more satisfying to do mathematically. I don't know why all this stuff's filled in. Let's take a look at this for a second. What does this mean? We talked about this the other day. So what does it mean for the limit of f of x as x approaches a to equal L? Well, we kind of talked about that in terms of the ants, right? It just means that an ant approaching a would always anticipate stepping on a certain y value, L. But we just looked at an example where that didn't work because there was a gap in the function. Ants from different directions would anticipate different things, right? So we could maybe ramp up our understanding and our definition of a limit just a little bit here. We could do something like this. We could introduce the notion of one-sided limits. Okay, what do you think it means and we're not going to do a lot with this today, but I just want to introduce this concept. What do you think this part right here means? Let's see. What do you think that means? The limit of f of x as x approaches a, and there's a minus sign there, equals L. Okay, that's it. That's from the left. How come? What is that? How does that minus sign indicate that? Well, that's telling us that we're approaching a from values less than a. Well, what direction would that be from on a number line? That would be from the left. Another way to think about it is it's from the direction of negative infinity. Okay, so this just means there's a one-sided limit from the left. Okay, similarly, you probably know what's coming then. How about that one? From the right. If x is approaching a, and we have a plus sign there, that's indicating x is approaching a from the right. Okay? So we can add this extension to understanding of limits, and we can now say that this original limit, which we could technically call a two-sided limit, can only make sense and exist if both of the one-sided limits exist and agree. If they both have the same value from the left and the right, if they anticipate stepping on a certain value, call it L, well, then it makes sense for us to define a limit there. So this guards against that first situation where we had a gap, right? Because that wouldn't work. In the case that we looked at with that gap, let's go back a little bit. You know, the limit as x approaches 0 from the left, the limit is -1. As x approaches 0 from the right, the limit of the function is +1. They don't agree, so the limit doesn't exist, because it can only exist if both of them, if both the left and the right exist and agree. Okay, give me thumbs on that. Okay. Oops. Oh, I guess that's it. Okay. Oh wow, this stuff is filled in. I guess I forgot to erase it. Okay, so real quickly, evaluate that limit for me. So what's the limit of g of x as x approaches -1? Just hold up fingers. Okay, good. Yeah, it's 3, isn't it? Good, because you guys are getting good at this. You're starting to ignore the fact that the actual function, the value of the function there is 4. The value of the limit is 3, and that's what we asked about, right? Because it's true that, well, you tell me, what is g of -1? That's 4, isn't it? Right? Good. But the limit is 3. Okay, so some properties of limits here. When are we out of here? 25. Okay. So this is stuff, just so you get a feel for this, this is stuff that's super intuitive and just common sense stuff. It's not like you even really have to spend a lot of time memorizing and thinking about this. The answers to these properties are exactly what you would think they would be, just using common sense. And we'll still go through them quickly. So some properties of limits. If we know that if the limit of x as x approaches c, it doesn't depend on the value of the function at c. It just depends on the value that we are approaching. However, oftentimes, the value that we're approaching is the value of the function there, right, at a certain place. Like, let's take an example. Like, what if we had, for example, oh man, let's see here. Let's just look at this example for a second here, right? Okay, so what's the answer? We don't even need a graph. And this is really simple. Now you're probably thinking, well, we get this, but what's the answer to that? What's the limit of the square root of x as x approaches 9? The answer is 3. How come? Well, look at the graph. Right, here's the graph of the function f of x equals the square root of x, right? You know a little bit about this function. You've dealt with that a lot over the last couple of years, right? You know that it's got a terminal point here at 0, 0, and then it just does this forever. What's the domain of this function? What's the domain of a square root function like that? Say it again. Okay, good. So we'd say if we wanted to use like interval notation, would I put a bracket or a parentheses there for the left endpoint? Put a bracket because it's including, it takes more ink to draw a bracket because it includes the endpoint, right? So it's going from 0 up to infinity, bracket or parentheses? Parentheses, because you can never include infinity, right? Okay, between 0 and infinity, every value is included in that function. Does it ever have any weird behavior where it jumps around? No, it's continuous, isn't it? Right? Remember talking about continuity in Algebra 2? Our rule for continuity was a function is continuous if you can graph the function without picking your pen off the board, which we can do, right? So we know then, we already know a lot about this without even having to think about what the graph looks like. What's our best strategy for taking the limit here? How could we know what value does the ant think it's approaching as x approaches 9? Well, it's that point right there, right? It's the point with coordinates x equals 9, y equals 3, right? So this is a case where the ant is going to step where he thinks he's going to step. And that's where direct substitution works, right? Why, if we're trying to answer the question, let me say this as clearly as I can. In taking a limit, we're trying to answer the question, where does the ant anticipate stepping? The easiest way to answer that question for a function like this is by saying, well, where does he actually step? Because that's where he thinks he's going to step, right? All we have to do is plug 9 into the function and get 3 for our answer. Everybody get that? Those kinds of limits are just super simple. Let's take another one. Like, what if we were going to take another function that we understand? It doesn't, like, well, how about f of x equals, x squared? Domain is all reals, right? It's continuous. There's never a place on this function where the ant wouldn't step where he thinks he's going to step. So you tell me, what's the limit of the function x squared as x approaches 7? 49, right? Because that's where the ant actually would step. So that's where he thinks he's going to step. You see the point? Okay, we're done for today. I'll put an assignment up. I'm going to put up a longer assignment in Math Excel that you won't be able to. On Friday, we'll probably finish this stuff up. And so but if you want to get a jump on that, that's fine. I'm also going to assign you can do it before spring break, but I'm going to assign a couple videos covering this from the AP classroom stuff. But if you want to get it out of the way before spring break like I would, I'll put them up right away so you can. Deal? All right, have a good day. How'd that go, Madeline? Was it good?
On the assignment, I turned it in, but it said I got 6 out of 9, but it marked one of them. I must have accidentally clicked it, but I tried to.
Oh, that's fine. I'll just.
But it said I clicked C, but also when I tried to turn it in, it said I didn't answer that one.
Okay.
It was marked.
Okay, I'll try to remember that when I input grade. I'm sure I will, but if I didn't, just remind me, Daisy, and I'll bump it up. So that should 7 out of 9. That should go in as 100% on that one. Yeah.